Thank you very much for coming here. We are always glad to host DEVCLUB and the old engineering community of Tallinn and Estonia. I want to speak today about the topic. This is the continuation of the topic I was speaking about 1.5 years ago at the same stage. It was hard to start speaking back then, and it was hard to start a machine learning project back then. Today, it is still hard to start speaking, but I hope it's a bit easier to start a machine learning project. For many companies, fraud detection becomes the main driver behind embracing machine learning techniques. TransferWise is not an exception. Our fraud prevention team started experimenting with machine learning in the late 2015, and we've put quite a lot of effort into it. And with this effort came experience that we actually want to share right now with engineering and data science community. Before diving into details, I wanted to introduce you what actually fraud detection is, because it's our example. TransferWise is a money transferring business. An individual given a credit or debit card can transfer money from one country to another just by knowing a credit card number. And if this credit card number was acquired illegally, then this individual is called fraudster. Fraudsters are statistical anomalies, and this is how we try to find them. Let me give you an example. Imagine not a young customer from US making transfer to somewhere to Russia with an Estonian IP. If you look at the picture, it doesn't pass reality check. Statistically, these kind of customers don't exist in real life, and there are just no good customers that have the same combination of parameters, and we try to find such parameters, and this is where machine learning kicks in. Machine learning is not a young field anymore. It has its roots in optimization, combinatorics, and these fields appeared long before transistor appeared. But it had limited application before internet scale volumes of data. And today, spam and fraud detection is already a classics of machine learning, where it truly shines. So for us, it was not a question whether we should start using machine learning or not. We just needed enough data to learn from. Here you can see the yellow bar. This is where we trained our first model. We had to collect quite a lot of data, labeled data, before we actually can train something. And while we were collecting it, we could easily and silently fix our technical debt problems, which I was talking about on my last speech at DEVCLUB. The first model that we built was built on top of our rule engine. In our rule engine, each triggered rule gives a score, and usually it's a hard-coded score. Then we sum the scores up and compare it to the threshold. If value is above threshold, we raise suspicion. It's a very simple thing, but it's sure the scores assigned to the rules and the threshold itself are not optimal. We tried somehow to think how we can optimize that, and came up with an idea that we just treat our rules as features of a machine learning algorithm. And we trained a machine learning, a random forest on top of it, and since then we never regretted that. And at this picture you can see a classical ROC curve for our rule engine. This is the blue line, and the new random forest model. So this was trained on Spark 1.6. It would immediately give us quite a good benefit. We either could decrease false positives by 30% or increase true positives by 10% with almost no effort. At least we were thinking so back then. Okay, so we've got our model. I trained it on my machine, but there is a chasm between your sandbox, where you play with machine learning, and the production deployment. There were gaps to fill in, and one of the major problems was the question whether we're actually using the right framework. I've chosen Spark just as a tribute to hype and fanboyism. I like it, but is it really something we should stick to? So we came up with a list of requirements to choose Spark ML machine learning framework. Sorry. So it should support saving and loading models. Models should support changing of arbitrary transformations using pipelines. Models have to be able to be loaded into JVM process so that we could run it in production in our Java environment. The framework should be scalable to scale up to hundreds of thousands or hundreds of millions or billions of examples. Python API would be a plus for sure. Prior experience with the framework is also a plus. And the last, but probably the most important thing, was that we wanted a single execution path during training and production when we are running models in production. So most of these are quite self-explanatory, but I wanted to draw your attention a bit more to the last point. So what do I mean by single execution path? There are three chronological steps in the life of every machine learning model. First, you do training, where you get the model itself. Then you run testing, where you run prediction on your test set and measure performance. And the last thing is the model gets to production, where it actually makes prediction and you make a decision on top of that prediction. At every step, data undergoes some transformations. And the hard part is to ensure that these transformations are doing exactly the same thing in on offline training flow and online production flow. It very often it is done so that one code base is used for training, for example, scikit-learn and Python code, and completely another for running in production. Let's say JPMML, which stands for Predictive Model Markup Language, whatever. And there is no maintainable way to guarantee that implementations of models in scikit-learn and this JPMML are actually doing the same thing. So, machine learning engineer ends up with the following options. To use one framework for all of this, or to use two frameworks, one for training and testing and another for production flow, or maybe to have one framework for training and another for testing and running in production. The first case, when there is a single framework, is the most desirable. For sure, it simplifies things. You don't need to care about compatibility between those frameworks, and updates to software becomes much easier, and you don't need to have parity tests between your frameworks. Second option, when you have your training happening in one framework and testing and online prediction happening in another, is kind of okay, but it puts additional effort on analyst. So he has to juggle two frameworks when training a model, while training and then testing, passing data between those is also quite difficult, and this burden lies on shoulders of data analysts, and depending on their coding skills, it may become unbearable. And the third option, when you have training and testing happening in one framework and the prediction happening in another, this is simple for data scientist. He stays within the same framework, but it requires some effort from engineers, because now you have to, when you deploy a model to production, you actually don't know what you deploy, because there is completely different execution path happening in production, and you need some facilities to test models in production. This is the reference to the title of my presentation. Luckily, this kind of framework to test models in production is very helpful by its own. You are not guaranteed from mistakes even if you are using one framework. So it also follows the best practices of gradual rollouts and A/B tests. So you first deploy model to production in the shadow mode. It runs for a while. You collect statistics, see that it works as you want it to, and only then you switch your production flows. The downside here is that is the feedback loop. You have to wait for a few weeks maybe to collect this statistics. Otherwise, you can't make a decision. At the point of time when we were choosing our framework, the only framework we found that supports all of these requirements was Apache Spark 2.0. And the problem was that it was not released yet. So we were thinking what to do, but okay, we thought, okay, running snapshot probably is fine. Okay, but don't try it at work. The only thing that we needed to do is actually to smartly mitigate risks. So we needed a proper monitoring of models that are running to see how they perform, what is their latency, speed, and actually the accuracy they give. Additionally, if machine learning process fails, there should be a safe fallback. In our case, it was our good old scoring rule engine. But even if everything fails, the machine learning models should not be put into a critical path, so that customers are still served even if everything fails. Surprisingly, it worked well. We didn't experience any issue related to the nature of snapshot nature of Spark 2.0. That was just, we were just lucky. But this is something I can't tell about the Spark in general. So we decided to go with Spark, but how we should run it. There are two modes that Spark can operate in. There is a cluster mode and a local mode. In cluster mode, every principal component of Spark runs in its own process. This requires quite a lot of orchestration and operational work, which we didn't want to have. In contrast, there is a special local mode that runs the whole, all the pieces of Spark in the single JVM process. And it is looking very appealing. You can actually put the whole Spark into a Spring Boot application and serve your models through HTTP API. There was one problem though, that this mode is actually designed for running tests, but since we're breaking bad with snapshot, who was caring? We decided to run it in local mode. It simplified everything. Releases could have been done using our existing facilities. No need to operate cluster. Package updates are simpler. Security surface is pretty much the same.
Do you mean only one instance?
So we are running multiple instances of microservices anyway. So, and there was a single Spark instance within instance of our microservice.
But still one instance of Spark application.
Yeah, within JVM process. Yeah. So we decided to go with Spark running in local mode within a Spring Boot microservice. And this is when we started, and we got problems, for sure, like anything. And it was known from the start that there will be some problems with latency. We made some tests. Every time Spark starts a task, it goes through all of these principal components, even in this local mode, and it takes quite a lot of time. Also, Spark has quite heavy task serialization, deserialization procedure, and with very large tasks that and machine learning tasks are quite heavy, like any one model can be up to several megabytes or even tens of megabytes, it could jump, the latency could jump up to seconds. For our first model, it was not that big. It was between 2 or 4 seconds, which was considered acceptable at that moment compared to, for example, our data gathering latency. What was a surprise for us is when we trained our completely new model, and this new model was not relying on our rule engine rules anymore. So it was a completely different set of features with a lot of categorical features that required string indexing, and the random forest itself was of a completely different scale. There was hundreds of trees with quite high depth. Yeah. And when this pipeline that we designed was just too big, and the latency just jumped to up to 30 seconds. And it was absolutely unacceptable. Additionally, when Spark submits this task, it creates a lot of small Java objects, and 1 or 2 gigabytes of them. And imagine this on every HTTP request. Basically, it was just trashing garbage collection, and we had, you can see at this graph, garbage collection pauses up to several minutes, and every day our services started crashing out of memory. So there was only one solution, just to switch it off. And so what? Game over? No. So there were 3 ways out of this solution. Just get rid of Spark, find another framework, another framework to rule them all. It was hard to choose Spark, and there's probably no or almost no other frameworks that support all the flows. Another option was, so we didn't consider this option, dumping Spark. So because the transition wouldn't be flawless anyway. Another option was to contribute to Spark to make it faster. By that time, I already knew some Spark internals, and I understood that it's just too heavy task for us to handle. There are several parties that tried to do that and still trying, including UC Berkeley and the Databricks, the developers of Spark itself. So we were left with only one option, is to have 2 frameworks running. So no single execution path anymore. And the obvious solution for Spark was to have mleap as a second framework to run in production. mleap is a lightweight execution engine for Spark models, and not only. It actually also supports scikit-learn now in TensorFlow. It doesn't support training. The only thing it does, it can serialize models, load them into production process, and execute them very fast. This framework matured a lot since we started our machine learning experiments, and it convinced us to try it. But what move to mleap mean to us? So, as I said, no single execution path anymore. But luckily at that point we already had this production model testing facilities, so we were running models in shadow mode as a routine by then. And yes, this is the looking back at our diagram. Spark was used to train and test models, and mleap to run predictions. Also, it was since mleap actually supports almost all of the Spark models and transformers, except one, SQL transformer, and which we were using in every model. So we had to rewrite all of our models, our feature generation, and retrain everything. Another thing is that it was clear that we will have to contribute to mleap, because there were some features in Spark 2.2 that we were waiting a lot, and mleap just didn't support them. So that was a good occasion to contribute to open source. From the bright side, we've got 50 millisecond latency compared to half a minute and pauses up to and crashes. And no GC problem whatsoever. Yeah, this is 95th percentile for peak load during the day. What other Spark issues I can tell you about? There are actually quite many small issues. I just have no time to talk here about them, so you can probably find me in corridors and ask. But one feature, not feature, problem that I wanted to say about is the random forest memory footprint. So we were hoping that Spark will let us scale to at least 100 million samples in a training set. But yes, Spark itself supports that, but the algorithm of random forest they have doesn't. With a 2-node Spark cluster with 60 gigabytes of memory each, we were able to train no more than 10 million samples. One thing that helped us, we switched JVM to G1 GC, garbage collection, and it helped. So we pushed, we could train up to 15 million records now. So luckily, work on random forest doesn't stop, and there is a ticket in Jira, Spark Jira, that they are working on to fix random forest. With all that said, you can ask a valid question. What if I were to choose framework today? That's quite hard question. The world of machine learning literally exploded during those 2 years. Many frameworks that were not touching machine learning before now include machine learning as their official part. For example, Apache Flink, which is actually a streaming framework. Many machine learning frameworks now ensure you that they support production flows. And one of them, TensorFlow, got a major update in the beginning of this year, and they have now Java API to integrate into your Java processes. Also, they include TensorFlow serving that you can serve models from Docker container. Also, Spark is not standing still. They have now plans to have low latency streaming, continuous streaming engine. They try to push it to version 2.3. I doubt they will able to do that, but they will try hard. Personally, I would probably recommend today to try TensorFlow. This Java API feature is just making things so different, and features of TensorFlow and some architectural decisions they made just feel right. To finish with, I wanted to give you some hints to choose a machine learning framework. First of all, there is no framework to rule them all. There is no framework that will solve all of your problems. Not all of your problems. Industry is just getting there. But keep searching. This is very important if you will be able to do all the paths in one framework. Never underestimate the complexity of production deployments of machine learning models. Data preparation, model handling, and all this stuff around constitutes probably 90–95% of all of the work you will have to do, and only left 10–5% is the actual fun of training. For example, we were not able to move significantly before we put 3 engineers on this topic. When choosing, look at the community. All machine learning frameworks and the whole field is evolving very fast, and if you choose a legacy, it can be a serious detraction. It's probably better to take some risk and mitigate that with monitoring and other tools. This may be a game-changing for you. And if you have someone in your team passionate about some technology in machine learning, give him freedom. Probably this will be fun for him, and he will work hard. And don't spend too much time on choosing. Anyway, there will be problems, and you will have to solve them. Yeah. Thank you very much. Your questions?
So, on the website, do I need to use it? No? Okay, on the website, Spark says that it's lightning fast, and it's 100 times faster than Hadoop. And you're saying that it's mega slow, so what's the trick here?
So, yeah, there is a trick. Fast means throughput, not latency. So, with Hadoop, latency is even lower, but Spark has quite low latency if you have big models. If you have just a small real-time ETL that just transforms, like makes a count of some integers, it's a very small job that submits to Spark streaming, and it's fast.
Oh, sorry. Thank you. So can you talk a little bit more about the domain sale problem? You were talking a lot about the machine learning engineering part, but about what made, what data or what features made the machine learning model perform better than the rule-based agent? What were the possible probabilities that they pulled out?
Okay, I understood the question. Thank you. So, when we were considering what to do with our rules to optimize them, I was staring at it for a few months, and finally I understood that it looks like logistic regression, just a hand-optimized logistic regression, and this is just a linear algorithm. So if you put non-linear algorithm, like random forest, it basically, no doubt it will find some corners that can be more optimal. Also, with our second model, the one that was struggling with latency, we completely changed our feature set. So it now included raw features that were input to our rule engine. And there it boosted our accuracy much more.
Okay. Well, there's actually more maybe. You are still a little bit stuck in statistics, in engineering, but actually maybe talk about the problem, about maybe the data itself. Or
the data itself.
If you know.
So I can say not that much about data because it's, you see, we are catching fraud here, and if fraudsters will know what we are actually using, they will be able to do their work more efficiently.
This one's also getting on the internet, so you know.
Yeah. Basically, if just to some examples, we use some features, and for example, source currency. When money is transferred, there is a source currency and target currency. These are obvious categorical features. Person name can be, email, age is actually the history of transfers, whether user already transferred has a transfer, for example, 2 months ago, which is already much less risky, and many things like that.
Can I ask one more question? Or does anybody want to go?
Why random forest, not neural network as VM?
Thank you for that question. First of all, random forests are very simple to use. So we were aiming to pick low-hanging fruits first, and random forest is just known to not overfit. We have quite a difficult domain in the sense that we have very imbalanced problem. So we have big class imbalance, like there are much less fraudsters than good customers, and random forests behave really well on that. There are articles in the internet covering the fraud detection topics, and every one of them gives performance for random forest as the best. Another option is actually gradient boosted trees. Is also tree ensemble, which also works best, good, and we are experimenting with that too.
Last question for this one. Anyone?
I can ask.
Yeah?
Did you do any more feature engineering? What I mean is, did you look at the data more and said maybe we can derive something that we don't have yet before actually applying the machine learning model?
Oh yeah, sure. The feature engineering here is like the most of the work actually. So you, I don't know, we have probably 100 or something features, and every one of them is hand engineered. This is not something you can do automatically at the moment of time. And I don't know if I give one example, another example of feature preparation. For example, there are categorical features that have too many categories. For example, you have a card number. There is a bin in front, 6 digits, and there are thousands of them, tens of thousands, maybe hundreds of thousands, and you can't just put this number into any machine learning algorithm because there are too many of them. If you want to encode them, there will be so many. The feature vector will be too sparse to handle by any machine learning. Maybe neural nets, I'm not sure, after like 1 billion samples. We'll see. But you have to do something with that. A random forest can't consume this kind of high cardinality features. So what we do, we actually transform them to ratio features. And this is this ratio. It's also called label averaging. So, for example, for one particular bin, we find how many good users they're using the same bin, and bad users, fraudsters, and calculate this ratio, bad users to good users, or all users, and provide it as a feature. This is it becomes now a continuous number, real number, and it's consumable by any algorithm. We sure lose some data there, but it's better than nothing.
Right. Thank you so much, Dmitry. Let's have a...
Thank you.